Hello, everybody. Tonight we're going to be talking about simple harmonic motion and oscillations. Okay. Now, both of those are going to pertain to why I happen to have a bobblehead Einstein on the screen. We'll come back to that in just a second. All right. So, simple harmonic motion. Gonna get over here with a highlighter. Simple harmonic motion, oscillation. You should be able to answer two questions by the end of this. The first question is, what is simple harmonic motion and how does it relate to a pendulum and a spring mass system? The second question is, what is the period and what factors affect the period of a pendulum and a spring mass system? Okay, so also what's a pendulum and what's a spring mass system? So the terms that you're going to need to know by the end of that you're going to have by the end of the evening are oscillation, simple harmonic motion, cycles, restoring force, equilibrium, period, frequency, and amplitude. All right, so let's get started first on what is an oscillation. Let's go back to that Einstein. So an oscillation is any back and forth motion. So Einstein's head bobs up and down. Can't really do a little bit. Bobs up and down here. We are seeing it's a vibration, really. So when it goes up and down, it's making an oscillation. It's vibrating. And as it moves from its initial position upward and then back, okay, that is what we call a cycle. It's a complete cycle. It's a complete return to its starting point. When something starts at a starting point, goes away and comes back, that's a cycle. Simple harmonic motion, though, is a special kind of oscillation. It's a special kind of oscillation that is caused by a restoring force. Now, this restoring force is most commonly found in a pendulum or spring mass system. So let's take a look at a pendulum. Okay, so here's a pendulum. And if we're not doing anything, it just hangs there, right? This position, we're seeing this part right here, this up and down bit, that is called equilibrium, that dotted blue line. And that's where if I pull this up and then I let it go, all right, you're going to see that slowly over time, it's going to be less and less and less. Actually, we'll see that better if I hit a little bit of friction. Okay, hang on, let's try it one more time. Just a little bit with some friction. Okay. Oh. Try it again. Got a little bit of friction just so you can see it. That's basically air friction. But over time, all right, it's going to want to get back to its equilibrium. You guys have seen this when we did the Newton's cradles. After a while, it goes back to just hanging down. The reason why it always wants to come back to this equilibrium position, this up and down bit, is because of gravity. Gravity is constantly pulling it to go back to its equilibrium position. That makes, let's scroll this up. Okay. Now that makes the force of gravity or the weight is the restoring force. Okay, so the restoring force is whatever force causes something that is oscillating to return to its rest or its equilibrium position. Okay. So we've discussed then that a cycle is a complete back and forth motion. And the way that those cycles are measured, or the way that they're compared to other cycles rather, is by the time it takes to complete a cycle. So if we measure the amount of time it takes to do this, there and back, that amount of time for one cycle is called a period. Okay, period has the letter capital T, not a lowercase, it's a capital T. And if you think of like a period of time, its units are in seconds. Okay. All right, so with that, we can go ahead and take a look for, there's a very common equation that matches this. I'm going to find my cursor. And that equation is right underneath all the other stuff I wrote. So just one second, see if I can get it. I don't want that. Okay, let's move this out of the way. That's a little better. Okay, here's our equation. So we're looking at period is equal to 2 times pi times the square root of L over G, where L is the length of the pendulum, and that is in meters. G is the acceleration due to gravity. Okay. So by looking at the equation, we can tell that the only things that are going to affect the period are the length, and the gravity. But I know you're kind of looking at this and you're going, okay, maybe, but what about that mass on the end? Okay, surely if we change the mass is going to make the period change. Well, we're going to go ahead and we're going to double check this. What we're going to do is we're going to go ahead and we're going to pull this up to, we're going to pull it all the way up to about 17 degrees. Heads up, for a simple harmonic motion on a pendulum, you don't want to go any more than 17 degrees. That 17 degrees, above that, there's other things that factor into it. You can find them, you can determine them, but it's kind of messy for where we're at, for just like introductory physics class. Additionally, this 17 degrees that we're talking here, right there, right, that degrees, that would be considered the amplitude. It's the maximum position out, okay? It's the maximum position out right here. And that is, dang it, that is our amplitude. In this case, it's in theta degrees. You can translate that to meters if you wanted to, but for now, knowing it's in degrees is fine. So back to our simulation. So we've got it at 17 degrees, and what we're going to do is we're just going to do two sets. We're going to go ahead. I've got a timer. Where's my timer? All right, and we're going to count 3 complete cycles, and we're going to see how long it takes. And then we're going to go and we're going to change the mass, and I can do that. If you can see where, hang on, there we go. You can see right here where my cursor is, that's where we're going to change it. So let's go ahead and get started. Again, we're counting 3 complete oscillations. And go. 1, 2, 3. Okay, so in 3 oscillations, it took 5 seconds. So I'm going to hit reset. Remember, 5 seconds, keep it in the back of your head. And I'm going to increase the mass to 1.5 kilograms. We're going to do the same thing, 3 oscillations. Whoops, hang on, that didn't happen last time. Do a full reset, just 1 sec. We're going to pull this up to 17 degrees, the same amplitude, that we had last time. Get that all the way up to 17 degrees. It's on pause. Get our stopwatch going. Okay, and again, we're going to count 3 oscillations. So 1, 2, 3. A little bit more then, but you can see it's still approximately 5 seconds. So I basically did 150% of the weight, or gave it 50% more weight, and the period never changed. It still took the same amount of time. Just so we can kind of see it, let's go ahead. So 5 seconds, all right? What happens if I take this 0.7 meters, which is what it currently is, and I'm going to knock it down to 0.4. I'm going to get this back out to the 17. We're going to reset. Now remember, at 0.7 meters, all right, at 0.7 meters, it went ahead and it was approximately 5 seconds. So we're going to try this one more time just to see it. And 1, 2, and it doesn't matter because I never hit the play button. One more time. Ready, go. 1, 2, 3. That was 3.9 seconds. So when we cut down the length, all right, when our length got smaller, our period got smaller. It took less time to complete a cycle. So back to the note page. what we want to get out of this is this stuff right here, okay? That the period is equal to 2 pi to square root of L over G. If my length gets bigger, so will my period. If my length gets smaller, so will the period of this pendulum. Okay, so basically more length equals more time or more period, and this is a direct relationship. So again, I think we hit all the big things. We talked about amplitude. We talked about angles smaller than 17 degrees. So basically, that's what the pendulum, that's how simple harmonic motion works on a pendulum. The next thing we're going to look at is the other example of simple harmonic motion, which is a spring mass system. Here's a picture of a spring mass system. Okay. Well, first off, what you're looking at right now, this is the unstretched length, or some might call it the natural. When you put a mass on it, okay, I'm going to hang this mass right here, where it would be, if it wasn't moving, is considered the resting position. Hang on. Or this is equilibrium. This green line right here, that is your equilibrium. Okay. All right, reading my notes here. Okay, so just like with the simple pendulum, we talked about the restoring force. So what's the restoring force when we talk about a spring mass system? I'm going to go look. We're going to come down here. That's not what I wanted. Oh, we're having lots of fun today. Okay. So right now, if I've pulled the spring down this distance, which by the way is called delta x, okay, when I let go, it's going to want to go back, okay, and it's going to go and it's going to keep going, and it's going to keep going, and it's going to come back up here, and then what's going to happen? Once it gets to this place or something like it, it's going to want to come back down. So what is causing it to want to go up or come back down? Well, that's the spring force. So for the restoring force for a spring mass system is the spring force. All right, basically whatever I do, if I pull it down, getting rid of some signs here, I think, or maybe I'm not. Okay. Oh boy. There we go. Got a bit acting weird there real quick. Okay. So if I pull it down, the spring force wants it to go back up. That is the definition of a restoring force. All right. So the period of a spring is equal to the period, is equal to 2 times pi times the square root of m over k, the mass divided by the spring constant. Now the spring constant, k, what that is, it's how easy it is to stretch a spring, how stretchy. Okay, if you've got a big K, it's tough to stretch, or it's tight. Little k, if you have a small k, okay, so if you got a small k, very stretchy. All right, now if you're looking at this equation, you can see that one thing that this does not depend on, it does not depend on how much I stretch it, okay? All that the period of a spring mass system depends upon is m, the mass, and k, that spring constant. Actually, if you want to know, that delta x, the amount that gets stretched, this is the amplitude, okay? For a pendulum, it's the angle. For a spring mass system, the amplitude is the amount that you stretch it. So again, what this is showing is that the spring mass, for the period of a spring, depends only upon the mass, and it depends upon, inversely upon, the square of the spring constant. That is all that matters. So we've talked about oscillations and simple harmonic motion. We've talked about cycles and restoring forces and equilibrium, period, and amplitude. The one concept that we're missing so far is frequency. Now, we'll talk a little bit about a frequency right here just because it matches up with period, but we're not going to spend a lot of time on it. It's going to come up a lot more in other topics. But what we need to know is that frequency is the inverse of period. So where period, okay, so period we know as how much time it takes to complete a cycle. Frequency is how many cycles happen in an amount of time. So the entire time we were talking about period, we could just have easily said frequency. It's just that for period, for pendulums and spring mass systems, we talk about them in period because it's the amount of time that it takes for the motion to be completed. Okay, so we're going to use that a lot more as we finish, but for now, that covers our video on simple harmonic motion and oscillations.